So problem 6.6 really represents our last kind of heat capacity problem that is using an experimental method to determine delta H. So before I do 6.6, I just kind of want to review the previous three problems so you can see how they're similar and related. So problem 6.3 had to do with figuring out the amount of heat that it would take to heat 125 grams of copper, increasing its temperature by 275 C. So in this case, we just used this equation directly. The next two problems kind of dealt with heat exchange between systems. And problem 6.4 was heat exchange between two systems in a physical way, that is a hot system and a cool system. So a block losing heat and water gaining heat. And we use that to solve for an unknown heat capacity of our solid. So again, I'm going through these problems quickly. If you want to see the details of each one of them, look at those videos independently. And problem 6.5 went through a chemical process, so the mixing of an acid and a base, and that chemical process released heat that caused our water to heat up. But again, we could think about the same type of a process where we have the heat of the solution that was gained is equal to the chemical heat that's given up by the process. And so then we could normalize that to the amount of material that was there. So we did a limiting reactant problem to go ahead and figure out the molar heat capacity. So again, we might know this, the absolute amount of heat given off by a system, but to contextualize or normalize it to, say, 1 mole of substance, we need to divide by the amount that generated that heat. And that's essentially what we did in that problem. All right, so our last problem here is a calorimetry problem. And so, again, I'll show you what's similar and what's different from this problem related to the other stuff that we did, but as always, I like pictures to help me describe what's going on. Okay, so in this case, we've got some dessert that the manufacturer is claiming contains fewer than 10 calories per serving. So one thing to make sure that we remember is when we see a big C, so this is what we call a big C calorie. A big C calorie, 1 big C calorie is equal to 1,000 what we call little C calories. So 1 food calorie is 1,000 heat calories. And so we'll have to kind of keep that in mind here when we're considering this. And we also have a unit conversion that will come into play, because we need to be able to walk between calories and joules. And so we know that 1 calorie is equal to 4.184 joules. So again, we'll use that unit conversion in a little bit here. But back to our picture here. So I'm going to have a little calorimeter here, and I'm going to draw in here that we've got 1 serving of dessert. So I've got a serving of dessert in my calorimeter. So this is a calorimeter. And remember, what a calorimeter is something where you actually burn something inside. So we're going to add oxygen to our calorimeter, which means we burn whatever's inside, so burn it. And when you burn whatever's inside, remember what you get is carbon dioxide and water and heat. And so the heat is what we're going to be measuring here, because we're going to have a final temperature of our calorimeter, and they give it as 26.779 degrees C. The initial temperature of our calorimeter is 21.862 degrees C. So our calorimeter heated up essentially the equivalent amount of the heat that's given off by our burning dessert. So importantly, our calorimeter has a specific heat capacity of 8.151 kilojoules per Kelvin. And one of the things I want you to note, if we look back at, for example, earlier problems, right? Earlier problems had specific heat capacities that had joules per gram Kelvin. They had a unit of mass in there. This one doesn't, and that's because this takes into account the heat capacity of the calorimeter times the mass of the calorimeter. So it kind of lumps these together because the mass of the calorimeter is not changing. It's a fixed parameter. So we lump these two together, and that becomes part of a massed heat capacity for the calorimeter. So what this really means is that we have a heat capacity that combines these two terms. All right, so we're going to do something conceptually similar to what we did in our previous problems. There's going to be amount of heat that's given off by our system. And again, our system was our combustion of our dessert. And that's going to be equal to the heat that's gained by our calorimeter. And so we're going to set these two equal to one another. So there's going to be a positive heat for our calorimeter because heat's gained. And we could say that this is equal to C calorimeter times delta T. And remember, I told you that the calorimeter heat capacity combines the specific heat capacity of the metal times the mass of that material. So we kind of combine those into one term. So it's, you know, we're not given a mass here, but that's not a problem because we don't need that mass. Okay, delta T, remember, is always T final minus T initial. And so that's going to be equal to, what do we have here? We've got 4.937 Kelvin. Okay, so even though these are again given in Celsius, the difference between these in Celsius is equal to the same as the difference in Celsius. Okay, so we can figure out that the heat gained by the calorimeter is 8.151 kilojoules per Kelvin times 4.937 Kelvin equals 40.24 kilojoules. Okay, so what we know is this is the energy given off by burning our dessert. So really what this is this is how much energy our dessert is worth. So what we need to do is we need to compare this to what the manufacturer is claiming. Okay, so we need to compare. And the manufacturer claims that the dessert is worth less than 10 big C calories or food calories. So right now we can't directly compare these numbers. Comparing 10 calories to 40.24 kilojoules, we can't really compare those. But we can, again, if we use this unit conversion. So what I'm going to do is I'm going to say, and there's a few ways that you can solve this problem. I'm going to say, how many kilojoules is this? Because then I can directly compare that to this. So see if this unit conversion makes sense. Okay, we've got 10 big C or food calories. 1 big C calorie is equal to 1,000 little calories. And again, we have 1 little C calorie is equal to 4.184 joules. That was a unit conversion I told you about, again, one that you'd be given. And we need to compare this to kilojoules. So again, we're going to have 1,000 joules is equal to 1 kilojoule. So my thousands will cancel there. And basically I get 41.84 kilojoules. So 10 food calories is 41.84 kilojoules. Our dessert was worth less than that. So the manufacturer's claim that the dessert is worth less than 10 calories is true.